Your birthday?
No, I was going to say it's actually it's the first day of the rest of your life. Hope you make the most of it. Let's look at this. How do you make OH a better leaving group? First way we looked at is protonating it. Another way to make an OH a good leaving group is to convert it to a tosylate. What's a tosylate? Or a mesylate or triflate. Mesylate or triflate you're not going to see in the textbook. Same thing though. Analogous. Tosylate's most common at this level. These will serve as leaving groups without the need for protonating, without the need for acid catalyst. A tosylate will be a leaving group without having to protonate it. This is a tosylate. The oxygen is the leaving group. The oxygen will leave this carbon. Here's the carbon that we're doing the substitution on. Instead of an OH, we have an O with all this. Tosylate is sort of shortened for a methyl. That's a benzene ring. With a methyl, that's called toluene. You can buy it at Lowe's. Solvent. Toluene sulfonyl. Somebody said, okay, toluene sulfonyl, let's call it tosylate. With a shortened. That's tosylate. This would be OTOS. O-tosylate. OTOS written like that. It's actually usually written OTS. I write it OTOS. You'll probably see OTS. That's a tosylate. A mesylate, O-sulfonyl, just methyl. The methylate, methyl sulfonate, mesylate. CF3 is a trifluoromethyl called a triflate. These are all the same type of thing. The oxygen is bound to a sulfonyl with essentially an R group, toluene, methyl, or CF3. These are great leaving groups, just as good as iodine and bromine. But ultimately, the oxygen is leaving the carbon. OH won't leave, these will. Now, we will also encounter things that look like this. Diesters of sulfuric acid are also very common as alkyl electrophiles. Why do we call this an alkyl electrophile? Because right here we have an alkyl group with a leaving group. Alkyl with an Lg attached to it. The Lg is the tosylate. Nucleophile will attack the alkyl and kick off the leaving group. This alkyl is electrophilic. Gets attacked by the nucleophile. These are also very common alkyl sources. This is called dimethyl sulfate. Why is it sulfate? Well, first off, in Gen Chem you learned that this here with two minuses is what? Sulfate. You could put sodiums here and have sodium sulfate. Or what if we put methyls here? What would we have? Methyl sulfate or dimethyl sulfate. This would be diethyl sulfate. But if you look at this, on that side, it's just like the ones above. Nucleophile can attack here, kick off the oxygen that's bound to the sulfonyl. I mean, if this over here was a toluene, and an aromatic ring is often abbreviated as a phi, if that was a toluene over there, we would have a tosylate. It really doesn't matter over there. So these act analogous to those. The reason that these are pointed out is because they're very cheap. Dimethyl sulfate, they're very cheap because they come from, what if these were H's on the end? What would this be? Sulfuric acid. These are the diesters of sulfuric acid. Very cheap, very good alkyl electrophiles, supplying in this case, a methyl or an ethyl. Nucleophile attacking the methyl, nucleophile attacking the ethyl. This would be your Lg. O-sulfonyl R group, Lg. Tosylate's the most common at this stage. We do a lab in sometimes organic one. We're not doing it this semester where we use diethyl sulfate. Okay, how do you make tosylates? You make them using tosyl chloride and pyridine. Let's look at that. We'll make that tosylate right there. That would come from reacting this alcohol with tosyl chloride and pyridine. What is tosyl chloride? Well, we know what tosyl is. I mean, tosyl is that. So what is tosyl chloride? It's just that. Chlorine there. That's tosyl chloride. What is pyridine? Have we seen pyridine before? I don't know that we've used it. We may have said it. Pyridine is a benzene ring. Instead of what's C here with a CH, we replace the CH with a nitrogen, and that's pyridine. There's a lone pair there, of course. Pyridine is slightly basic. Lone pairs in an sp2 orbital. Pyridine's your base here. Pyridine's a pretty good solvent, pretty good reagent. Unfortunately, it has a nasty habit of causing testicular cancer. So watch out for that. Right, John? How do you get this? Well, look at what's going on here. The oxygen replaces the chlorine. If the oxygen replaces the chlorine, what do you get? You get that, but you also have to lose the H. If you look at this, we also produce HCl. The base picks up the HCl. Now this mechanism, the book probably will show it wrong. That's because they're lying to you. They don't want to tell you the truth until you get on over a couple of chapters more. I don't know that I want to take the time to go through the exact mechanism. We'll do this at the beginning of Organic 2. To get the oxygen to replace the chlorine is obviously a substitution. But it's not SN1 or SN2. Because if this was let's pretend that was a carbon. Don't do anything on your paper. Can you do SN1 or SN2 at such a carbon? Well, first off, we got a Nobel Prize because that's like 8 bonds from carbon. It's the same thing. You only do SN1 or SN2 at a tetrahedral carbon, at a saturated carbon. This is not a saturated sulfur. There's pi bonds there. You don't do SN1 or SN2. It's a substitution. But it's a mechanism we haven't covered. You can do substitutions by other ways. We'll learn other ways in Organic 2. I'm not going to go into the mechanism here. Also, chloride reacts with alcohol. Importantly, the chemistry just involves the oxygen reacting with the sulfur and displacing the chlorine. No chemistry takes place here. So there's no stereochemical change here. So if we look at this example here, if we have this alcohol with stereochemistry, what is that? That looks like S. Yeah? If we reacted with tosyl chloride and pyridine to put the tosyl on the oxygen, there's no change at this carbon. Why would there be? We're not doing any chemistry at that carbon. The chemistry is taking place between the oxygen and the sulfur. So that's important there. Now if we come in and do an SN2, we know that tosylate is a good what? Leaving group. That was said about 5 times above. We have a nucleophile. What's a nucleophile going to have to be a nucleophile? It doesn't have to be negative. It could be neutral. Lone pair. What does the lone pair do? come in, we're doing SN2, it says it right there, backside attack, kick off the leaving group. What type of stereochemical consequences do we have?
Inversion.
Inversion. This should now be R, assuming the nucleophile has similar priorities as the leaving group, which it does not have to have, but R, we get inversion. Regardless, it's inversion. Then we would get the inversion. There's no inversion back over here, is there?
No.
We didn't do any chemistry at the carbon over here. Now let me go ahead and introduce this. We could, how do you make this a better leaving group? One way is to convert it to a tosylate. That's what we did. What's another way? Protonate it. That's another way. So you have 2 ways to put in your toolbox. What's another way to convert this to a better leaving group? Well, it's sort of ingenious. But what if we react this with HBr and convert it to the Br? Plus what? Well, this is actually not a new way. It's sort of a new way with another new way in there. Plus what? Plus water. Yeah. What's the mechanism? How do we make this a better leaving group in this mechanism? Strong acid, OH, protonated. Yeah? Protonated. And then the Br minus. What can happen next? Attack here, kick off the water. What does that give? Gives this here. But what mechanism did we just do? SN2. So I actually didn't just convert it to a new leaving group. I actually protonated it to get it to do this. But actually now, we have a better leaving group. Now if I react this with nucleophile, with an SN2, what do I get? This comes in here and we get what?
Same stereochemistry.
We get nucleophile, but the stereochemistry will be inverted again. And this product is different than this product because in this scenario we only had one inversion because getting a better leaving group didn't involve inversion. But here in this scenario, how many inversions did we have? We inverted going to the bromine and then we inverted again when the nucleophile replaced the bromine. So this over here was 2 inversions. Just pay attention to how many inversions you're doing. Everybody agree that this first step there's no inversion? Because there's no chemistry going on here when you make the tosylate? Other than that, there's really nothing new. I mean, obviously there's an inversion here if you're doing SN2. Now you could have did SN1 here maybe, but I sort of showed you that we're doing SN2 because I showed you inversion and I showed you SN2. So that's tosylate. Mesylate and triflate are actually sort of better than tosylate, but you'll never really see these at the introductory level. Triflate's like the most reactive. Questions about tosylate? So up to now we've been looking at the electrophile. The substrate of the leaving group. We look at variation in that. Now let's look at variation in the nucleophile and what that does to the rate of SN2 reactions. So we know nucleophile is going to have the lone pair. It's going to be doing the attack. It either does backside attack or it attacks a carbocation. Nucleophile. First statement we can make is anions are more nucleophilic than the neutral counterpart. Hydroxide is more nucleophilic than water. Both of these would give an OH on the molecule. Here you'd have to lose an H. This is more nucleophilic. What's a nucleophile? Nucleophile likes plus charge. Which one's going to like plus charge more? Obviously, hopefully, you see it's hydroxide, yeah? But the fact that we're comparing these is an important consideration. The fact that both could possibly be used to give an OH on the molecule. And so a lot of times, very simple things need to be thought about. Okay, why do I need to know this? Where is this going to come up? As opposed to just memorizing, that's more nucleophilic. What's the purpose of looking at this? Which is more nucleophilic, NH2 minus or ammonia? Of course, everybody knows how many lone pairs are on these, right? Which one's more nucleophilic? Anion, right? So, anions are more nucleophilic than the neutral counterpart. Okay, let's consider different atoms. A less electronegative atom has the more nucleophilic lone pair. Which lone pair is more nucleophilic? Now the fact that there's two there doesn't mean a thing. Which is more nucleophilic? Now here we don't have a minus and a neutral. We're not doing that. We're looking at just atoms. Less electronegative atom has the more nucleophilic. Which one's less electronegative, nitrogen or oxygen? Nitrogen. So it has the more nucleophilic lone pair. It's more nucleophilic. Why? Well, in parentheses, I tell you why. Now we've talked about this before. We've used the same argument to argue different cases in the courtroom. No matter what argument you're making, nitrogen is a bad parent compared to oxygen. Oxygen holds its lone pairs tight, right? It's more electronegative. Holds the electrons tighter. Why does it hold it tighter? Well, you learned that in Gen Chem. There's more protons in oxygen and they hold the minuses closer. There's more attraction. Nitrogen's a bad parent. It doesn't hold the lone pair tight. It lets its lone pair get out there and do backside attack. Right? It's the same argument. Ammonia is actually a pretty good nucleophile, even though it's neutral. Because it's such a bad parent. That's a good nucleophile. If that's good, how good is that one? That's a very good, strong nucleophile there. So that was an example in the same row. We did this same type of stuff when we did acid-base chemistry. Which is a better nucleophile, H2S or H2O? Which one's a better parent? O holds them tighter, more electronegative, right? Not only does the sulfur not hold them as tight, but the lone pairs on sulfur, because they're in a bigger orbital, are further away from the atom. I mean, if I'm going to do backside attack, Crystal, which is going to be better to do a backside attack? Lone pairs that are out here and like, here I come, or lone pairs that are over here. And it's like, I got to get closer and all this stuff, and boom, lone pairs out here ready to go. These lone pairs are out there. Oxygen's a better parent. It's the same argument, but the electronegativity, now we're going down, right? Electronegativity increases as you go up and across, right? Which is a better nucleophile, I minus or F minus?
I minus.
I minus. F minus holds the electrons closer. not only because of the charge attraction, nucleus versus electrons, but also just orbital size. Those iodine electrons are way out here. Iodine is your best leaving group. It's also your best nucleophile for the halogens. And the reason it's best leaving group in nucleophile is really the same reason. The electrons are out there ready to move in backside. But also, if it's on a carbon, it's already kind of further away and it's a weaker bond. So it's easier to just get kicked off. It's a weaker bond. So it's inherently both a good nucleophile and a good leaving group. F- is a pretty lousy nucleophile. That's why when we were doing hydration of alkenes and we wanted water to add, we could use HF. But you didn't want to use like HBr. Because when you use HBr, Br would add to the cation. F- doesn't like to add to cations. Those lone pairs are just held tight. There's actually a lot of research that goes into trying to get F- to be a better nucleophile and to do chemistry with F-. Let's look at another effect. Any questions about those? Another effect of nucleophile, sterics. A sterically crowded nucleophile is not as good for SN2. If we look at this for the electrophile, it's the same argument for the other species. I mean, if you got a nucleophile coming in to react with something with a leaving group, we already said you don't want to have a lot of substitution over here because it blocks the nucleophile from coming in. And indeed, if this was tertiary, you would never do an SN2, right? Well, the same thing goes here. If your nucleophile with the lone pair starts having big substituents on it, these things are going to block this lone pair getting back there. And so we're looking at this portion. Look at this series here. This primary mean is going to be more nucleophilic for an SN2 than this secondary mean, and that's going to be more nucleophilic than the tertiary mean. This tertiary mean has 3 ethyls, and those are big. If I had 3 arms, it'd be like this. And if I've got these arms and the lone pair is right here in my chest, it's like, boom, I can't get there because the ethyl group is blocking. But if the ethyl wasn't there, the lone pair could get in there and attack. It's like pulling a big old jet into a small hangar. With those wings on there, it won't go. You take the wings off, then the jet can just move right in. Hopefully this makes pretty, this is pretty intuitive. Now I know somebody's thinking, well, what about induction effects here? Because we're talking about the lone pair being nucleophilic. The more electron density after the lone pair, the more it's going to go attack the plus. Which lone pair, which nitrogen has most electron density on the nitrogen? Actually the tertiary, because you got all these groups donating. And this is like high electron density. And then you might say, well, since it's high electron density, shouldn't this be more eager to go attack this partial plus, or maybe this is a bromine? And that'd be a reasonable argument. Unfortunately, that doesn't match results in the lab. Results in the lab tell us that this is the most reactive. So you have to change your argument. What would make this more reactive? Lack of steric congestion. Does anybody have another argument of why this is more reactive? It's not electron density, it's steric congestion. So, Which is more important, sterics or electron density?
Sterics.
Okay, that's what you have to take. That's your take-home message there. Now, I kind of lied to you because which one may actually be the best? Actually, the secondary may actually be the best. But it's okay to go with this one. Why is the secondary actually the best? Because it's the best combination. It doesn't have 3 groups, so it's not that steric, but it does have extra donation, so the electron it's a combination. It's a happy medium between having high electron density and less sterics. For us, I'd be happy for you to say that this is kind of close, because these are pretty close. But I think this one wins out by a nose. So we have 2 arguments, counter-arguments. You need to be able to make them both and understand both. But then how do you get your final answer? You have to base it on results in the lab. What's the evidence? Questions about that? In the end, sterics hurt SN2. Now, in this case, the substitution was right on the atom with the lone pair. In the next example, the substitution is not on that atom, but an adjacent atom. We can have ethoxide, isopropoxide, or T-butoxide. The substitution is increasing is actually on the carbon, not the oxygen. But it still is an effect. And terbutoxide tends to be non-nucleophilic. Tertiary amines tend to be non-nucleophilic. They're too sterically crowded. Non-nucleophilic is actually often used as a non-nucleophilic base for E2 elimination. Next week we'll be covering E2 elimination when we get to elimination reactions. And we'll refer to terbutoxide as a base that could be used. Because it doesn't like to do substitution because it's too sterically crowded. This is not. Of course, if you had an O with just an H, well, that would even be less sterically crowded because at least, this is a CH. There's no sterics here. No sterics, mild sterics, medium sterics, lots of sterics. Some terminology here. A molecule that attacks an H is called a base. A molecule that attacks any other atom is called a nucleophile. In both cases, you're using the lone pair. But an important difference between bases, attacking H and attacking other things. Sterics do not affect base strength. Because a proton is so small, it doesn't matter if there's steric crowding. So for example, this is a poor nucleophile. Why? Because of sterics. But it's a great base. Why? High electron density because of that donation. See, sterics doesn't matter with base when you talk about base because attacking an H, when you attack an H, sterics doesn't matter that much. The H is so small. Also, we don't have to do a precise backside attack when we attack an H. The H is a 1s orbital. You can attack it from many directions. The fact that you do backside means you have to come in. You can't just come in any other way. You have to come in backside. And it has to be right through here. And when you have a more confined attack, if you have wings on it just all limits. Okay, another thing to look at the nucleophile. Again, a lot of this correlates when we looked at acid-base strength. So that's an important difference between bases and nucleophiles. Resonance. Which is a stronger nucleophile? This O minus or that one? Which is going to be more willing to attack this partial plus here and kick that bromine off? We're talking about SN2, right? Let's see. Are we talking about SN2, Camille? Ah, yes. G, SN2. Yes. Which one's going to be more willing to attack it? Does it make sense if the one with the more minus? Which one has more minus on the oxygen? This one. Does this one have a full minus on that oxygen? No. This one really has what? It has a resonance structure that looks like that. What's the true structure of this species? Partial minus, partial minus. Which is going to be more willing to attack here? Now, take your choice, whichever one, but it's not a full minus. A full minus or a partial minus? Full minus. There's no charge delocalization here. This is charge delocalized. Now, I could have asked the question, which anion is more stable?
The one on the right.
Now, this one. It's more stable because it's delocalized. The fact that it's more stable is also a good argument for it. It doesn't want to do much compared to the other. It's happy. It's not as... This one must have become neutral. This one's like, well, I'm fine. I'm delocalized. So there's a couple of arguments you can make. A conjugated or delocalized lone pair is not as reactive. But it still can react. Particularly when it's an anion. What's the name of this guy right here? Elena Webb? Acetate. Learned it in Gen Chem, right? Acetate can be a nucleophile. But it's not going to be as strong as ethoxide. Which is better nucleophile? Aminocyclohexane, or what do you want to call this? Aniline. Which is more nucleophilic for SN2? Nada? First one? Yes, why?
The second one has resonance most.
Because is this lone pair sitting right there on that nitrogen, or is it delocalized into the ring by resonance? Yeah, we can draw resonance structures, right? We've already drawn resonance structures of aniline. And actually, if you draw resonance structures, you see that that nitrogen of aniline actually has what type of charge on it? And the hybrid looks like partial plus, partial minus, partial minus, partial minus. There's the true structure. That nitrogen actually has partial plus due to resonance. Is a partial plus going to want to attack this partial plus? But over here, this lone pair is sitting right there. It's not delocalized at all. There's no p orbital next door. It's sitting right there on that nitrogen. There's another argument we can make, or another way to say the same thing. What type of orbital is this lone pair in? Elena Hall? Elena Hall? Brianna? What type of orbital is this lone period? We spent like two lectures on this back in August, September. Why did we do that? Because we need to know such. I mean, we're going to move on in. What type of orbital is that in? SP3, right? What type of orbital is this lone pair in? It's in a p orbital. Somebody said SP2. If it's in SP2, you can't do resonance because you only do resonance with electrons that are in p orbitals. I think that's rule number 1. But hopefully we learned, I mean, that's why we learned such back in August and September. We also said that a lone pair in a p orbital is typically not that basic. Well, it's also typically not that nucleophilic. It's busy doing resonance. It's not interested in doing any backside attack. Resonance effects. Hybridization effects. Well, what type of orbital is this lone pair in versus that one? Hey, what's the name of that guy? Ogechi? What's the name of this molecule? We saw it at 10 after 8. Pyridine. What type of orbital is this lone pair in? sp3. How about this guy? It's not p orbital. sp2. I would recommend graphing it. Okay. Understanding lone pairs, hybridization, that's fundamental to organic chemistry. That's like first having to learn your alphabet before reading. And learning how to read before you can write, and learning how to write before you can compose symphonics, Beethoven or whatever. And so it's progression, right? sp2. So, which lone pair is held tighter to the nucleus? Held tighter to the nucleus. Right? So which one's more willing to get out there and do backside attack? This one. You could say, which nitrogen is a better parent? Which one holds its kids closer to home? It's a better parent. Holds them tighter. It's not as good a parent. Hybridization effect. See how this stuff is sort of analogous to the same considerations for acid-base chemistry back in August and September? In fact, you should look back at that handout. But just remember, you do have the difference between a proton and something else, as I mentioned here. Rank each of the following according to nucleophilic strength, from weakest to strongest. You guys on the left do number 1. You guys on my right do number 2. Put them in order from weakest nucleophile to strongest.
Or it should be H2O and NaOH. I would assume that NaOH is from but because H2O is coded.
Okay. Courtney, what's the weakest nucleophile in number 1? Tell me again. I thought I heard water. I can't hear. Too many Bon Jovi concerts. Water? Go with water. I'm thinking water. Anybody else? What's the weakest one?
Sodium acetate.
Why is sodium acetate not water?
This is not stable resin.
Yes, it is resonance delocalized. And so this oxygen is only what? Not full minus, but partial minus. But that's a partial minus charge. Well, you could say, well, you got dipole here. Here's the take home. This is an anion still. Even though it's delocalized, it's still an anion. And an anion is going to be, yeah, you kind of have apples and oranges. Yes, it's delocalized, but anion is still, in general, I would say the anion. Especially since it's oxygen and both oxygens. I could probably show you one where, if I showed you ammonia, then I would probably say ammonia. But we also have a difference because nitrogen is the worst parent. So I can see there's some questions there. But in the end, for me, the take home is it's still an anion. Oxygen anion versus neutral oxygen. The weakest is water. I'm going to call that 1. We're going from weakest, right?
Yeah.
What's next?
Sodium acetate.
Well, let's compare. Is sodium hydroxide stronger? Yeah, that's stronger.
That's food.
Let's consider Let's consider this. We can make this rank. Which is stronger, hydroxide or SH minus?
SH.
Yes, this. They're both anions. What's your argument?
That's bigger.
Bigger. Also, just not held this type. Worst parent. Less electronegative. So this is going to be ranked here. We have the 4 here. If that's the better than that, that's better than this. Is this better than this? Full minus or delocalized minus?
Full minus.
This is the strongest. So it's easier to go from strongest to weakest. So this is going to be number 4. That's the strongest. Which is stronger? O minus or S minus? Hold on. We just got that wrong. That's not right.
Yeah. Your SH.
No, SH is stronger. This is number 4. It's called. We should say strongest to weakest. That would help me better. That's the strongest. Now we're saying what's next? Which is next stronger? This is stronger than that. Is this stronger than this? Yeah. Because it's a full minus. That's a neutral. This is a partial minus. This should be 3. What's next? I said this was stronger than that, so that's 2, and that's 1. Is that right? 1, 2, 3, 4. With 4 being the strongest.
Yes.
Yeah. This illustrates the fact that sulfur is a great nucleophile. Because it's bigger, it's not as electronegative as oxygen. Oxygen's a better parent. Your body uses sulfur as a nucleophile all the time. When you get to biochem, you'll see sulfur nucleophiles. Good nucleophile. Even in the neutral state, it's pretty good. How about the next one? Let's start with strongest. For me, that's easier. I'll change that. Shantia, which is the strongest nucleophile down here? Or weakest, whatever you like to tell me. Which is on the end? Precious, which is strongest or weakest?
KCl.
Strongest? So you're saying Cl minus is stronger than NH2 minus? Why are you saying it's stronger than NH2 minus, for example?
I'm looking at size.
Yeah, but size is only important when you're going straight down a group. Which is stronger nucleophile, Cl minus or F minus? Cl minus is stronger than that.
So it would be
O minus is?
the
Which is stronger, O minus? There's no resonance in any of these. O minus or N minus? This is going to be your strongest up here. That nitrogen is not that electronegative. This is your strongest, so 1, 2, 3, what's that, 5? That's your strongest, 5. Basically, as you go across, you're getting less electronegative. The oxygen is going to be next. Which is stronger nucleophile? O-methyl or O-T-butyl? Stronger nucleophile. I didn't say stronger base, I said stronger nucleophile. Stronger nucleophile. Sterics hurts nucleophilic strength. This is a stronger base due to the donation. Weaker nucleophile. 4. Then that one becomes, this would be stronger than Cl minus. What's another way we could argue that this is weaker? We could say, well, if we had HCl, or if we had T-butanol, which one is more willing to give up an H and become minus? Which one's a stronger acid? HCl, which is one of the 7 strong acids, or T-butanol? HCl. Strong acid. Strong acid means the anion is happy to be an anion. It's pretty stable. This guy is not as happy. Why? Because oxygen doesn't like minus as much. Now you also have the size thing. Basically here, O minus is going to be stronger than that. But Cl minus is stronger than F minus, so this would be 2 and 1. Cl minus is bigger, less electronegative than F. Size is really important when you're going up and down. If you're kind of coming across electronegativity, I would rank them like this. Was there a little bit of new there? Yeah, there's a couple of take-home messages there. Please look ahead, summing it up. And we're going to start doing more precise examples now. Please look through this, and where there's reactions, try to think about reaction products and stuff. And we'll move ahead on Friday. Shaken Not Stirred this week. Group lab report due in lab. SI today at 3 o'clock.